Okay, so pairing of electrons. Whenever electrons are paired in a complex, there has to be an energy spent which is known as the pairing energy. So the pairing energy, it is denoted by P. Now if the value of the delo, which is caused by the ligands, if the splitting which is caused by the ligands can overcome the pairing energy, then pairing will occur, because this is also a type of energy itself. If this energy is greater than the pairing energy, then pairing will occur. However, if the value of delo is less than P, okay, then pairing will not occur. So from there we can get our concept of the strong field ligands and our weak field ligands. We have seen in our spectrochemical series, on the left hand side those had less value of delo, right? The magnitude of the delo values for those ligands were less, those which were on left hand side, and those which were on the right hand side, for them the magnitude of delo was high, right? So they can maybe overcome the pairing energy, whereas the ones on the left, they cannot overcome the pairing energy. So this is the concept of your pairing. Now we have a question. In this question it states for Mn3 positive ion, the electron pairing energy is 28,000 centimeter inverse. Okay, Mn3 positive pairing energy is 28,000 centimeter inverse, and it is telling me that the delo of the complex MnH2O whole 6 3 positive is 21,000 centimeter inverse, and the delo of the complex MnCN6 3 negative is 38,500 centimeter inverse. Which of these complexes is high spin? Now if you remember, high spin complexes were those complexes in which pairing does not occur. So high spin means no pairing. And when will pairing not occur? Pairing is not going to occur if the value of delo is less than P. So P is 28,000 centimeter inverse for Mn3 positive. In both of these complexes, the manganese is in a +3 form. Okay, you can calculate the oxidation number state and you can see that both of these complexes are in +3 form. So we can compare both of these complexes with the same pairing energy. For the first complex, the value of delo is less than P. But for the second complex, the value of delo is greater than P. So for the second complex, it can be low spin. So our second complex, that is the MnCN6 3 negative, that is a low spin complex, because for in it pairing can occur, because the delo is greater than P, the delo can overcome the pairing energy. But for the first complex, that is MnH2O whole 6 3 positive, for that pairing is not going to occur because the delo is less than P. That means it is a high spin complex. So the correct option is option B. That is, option B is a high spin complex. Now pairing of electrons, or the concept of strong field or weak field ligands, it is applicable to some of the configurations and it is not applicable to other configurations. Like if we talk about D1, D2 and D3. Like if a metal cation has a D1 configuration or a D2 configuration or a D3 configuration, that is I am talking about the inner orbital 3D. 3D1 or 3D2 or 3D3. This is my 3D then. Let's fill up electrons in this. So what we need for octahedral complexes? For octahedral complexes we need 2 d orbitals, right? Dx square y square and dz square. So if the complex or the configuration is already D1, D2 and D3 and 2 orbitals are already we are getting for the lone pair of the ligands to go into, why do we need to pair up? There is no need for pairing up. So if there is no need for pairing up, then pairing will not take place. And if pairing does not take place, that means the concept of strong field ligands and weak field ligands will not exist here. Because for 3D1, 3D2 and 3D3, it does not matter what ligand is present. There is going to be no pairing. So no ligand is strong, no ligand is weak in case of the configurations D1, D2 and D3. Similarly, the weak field ligands and the strong field ligands, they do not have any effect on the complexes of configuration D8, D9, D10. Again, let us make our d orbital, 3d orbital, and we fill in electrons in our 3d orbital. So let us start with 3d8. 1, 2, 3, 4, 5, 6, 7 and 8. 2 electrons are unpaired. That means these electrons can pair up. But what do we need for octahedral complexes? We need D2sp3. That means at least 2 orbitals of D should be present. Even if I am pairing that electron, even if these electrons I pair up, that is only going to give me 1 d orbital. So that is still not going to give me 2 d orbitals. So I can still not make an inner orbital complex. Now let us increase an electron and make it d9. Now I cannot pair up anything at all. Okay. D10. Again, nothing can be paired up even if a strong ligand is present, even if a weak ligand is present. So in case of D8, D9 and D10 configurations also, the strong ligands and the weak field ligands, they do not have any effect. Because in case of D8, pairing can happen, but it will not give you octahedral configuration. And in case of D9 and D10, pairing cannot happen at all, even if it is a strong field ligand present. So that brings us to the question, where can be the concept of the strong field ligands and the weak field ligands applied? To which configurations this concept can be applied to, for which configurations we can see that which ligand is going to cause pairing and which ligand is not going to cause pairing. So that answer lies in the next slide. The weak field and the strong field ligands, they affect the d orbital configurations of D4, D5, D6 and D7. That is the D4, D5, D6 and D7, they can pair up this is D5. So if I pair up electrons, then I can easily make the orbitals empty for a D2sp3 configuration. Similarly for your D4, D6 as well as D7. So in that case, we can apply the concept of strong field and weak field ligands. That is, in case of strong field ligands, pairing is going to happen. In case of weak field ligands, pairing is not going to happen. Because here we can get a different D2sp3 or an sp3d2 depending upon the delo of those ligands.